Testing, testing. Okay, it shows on the road. Okay, so we're going to go through uniformly accelerated motion in one dimension. All right, so we've gone through acceleration being the slope of this, this motion. So the velocity time graph, the slope of velocity time graph is acceleration, so we've got that there. We also established that we have the average velocity is the average of the two velocities, so the sum divided by 2. Okay, so that's going to be useful. All right. So we're basically going to come up with 3 equations that govern a lot of questions involving uniformly accelerated motion, and we'll go through some examples as well. So first of all, let's get my derivation 1. All right, so we're just going to basically just rearrange the first one. So the first thing we wrote was acceleration equals final velocity minus initial velocity over time. If we rearrange that, we're going to multiply the time across, so AT equals V, take V naught. And we're going to take that vector across the other side. What you also notice is I've actually dropped the vector signs from these. They're still vectors, but well, what we've been doing is if we had vectors in one dimension, we've been using positive signs for one direction and negative signs for the opposite direction. Okay, so that's our first equation. Final velocity equals initial velocity plus acceleration times time. Okay, so that's equation number 1. All right. Now, equation number 2 comes from your good old distance equals speed times time. But what we're going to do is we're going to call it average velocity times time. Okay, it's auto-focusing for some reason. I told you to go manual. Oh, no matter. There we go. Okay, so what we find is if we have uniform acceleration, then the average velocity, like think about it this way, if I draw a line across here, okay, the area under that line is the same as the area under the blue line. So what I just drew there was essentially the average velocity. Does that make sense? So this still works if we use the average velocity. Now we discovered what the average velocity was. It was v plus v naught on 2. So we can write that. Times time. All right. Now we also know that final velocity is AT. Okay, so final velocity from what we've discovered in this equation okay. Oh, sorry, I've also forgot the U. So V naught. It's V naught. So final velocity equals initial velocity. Sorry, final velocity equals initial velocity plus acceleration times time. That's what this is. So I've basically taken that and I've substituted it in place of final velocity. All right. Now, I'm just going to tidy that up again. So one more line. Take the division of 2 at the front. And I've got 2v naught, 2 initial velocity, plus AT times t. And then I'm just going to expand that. That would be S equals v naught t plus 1/2 AT squared. All right. Okay, so that's our second equation. Sorry, you couldn't see that. All right, so there's our second equation. So what that one says is, okay, distance traveled, sorry, displacement, this needs to be vectors, definitely in the cases where when you've got vectors in opposite directions. Displacement equals initial velocity times by time plus half of acceleration times by time squared. Yep, can you see that? So, sort of, okay. I might move that down a bit. Okay, there we go. All right, there you go. Yeah, I mean, you have access to this. I'm going to write these all up on the board. So you don't, the final formulas I'll definitely write up on the board in a minute. Okay, so yeah, I mean, you can transcribe this if you want, but it's all in the book. It's all on page 57, so you don't have to write the derivations down. You can if you want to, but I don't think it's necessary. So that's equation number 2. Okay, and the last one we do is a combination. The derivation 3. Look, especially using this combination, I don't think I'll do that derivation. You can see it on page, I'll let you have a look at that yourself on page 57, because I want to go into some examples. You can combine the two of these, or you can start again. I think they do it a different way. On page 57, you get another derivation which goes like this. This is the end result. V squared equals V naught squared plus 2AS. That's equation 3. Yep. So that one says final velocity squared equals initial velocity squared plus 2 times acceleration times displacement. Okay. So now I've gone and summarized all of these over here. Okay, so there's your 3 Newton's equation of motion in the order that I did them in. Okay, the first one, yep. V equals V naught plus AT. S equals, second one, S equals V naught T plus half AT squared. Let's fix that up straight away. I don't have my Sharpies on me, so that has to be in pencil. So yeah, T squared, sorry, that was a mistake. And final velocity squared equals initial velocity squared plus 2AS. Okay, the way you go about using them is if you've got a problem like the ones we're going to go through, you data mine the question for all the information you have at the start. Some of those might be numeric values, some of those might be in words like at rest, which means 0 velocity. So you might start at rest, you might end at rest. So you might have your initial velocities at rest, and that's V naught, or your final velocities at rest, that's V. It may be a problem involving vertical motion, which we'll come to in another lesson. So I'm just going to do some just some problems that don't involve gravity at the moment. Okay, and you may have displacement. So you mine the question for the information that you have. Then you look and you see, okay, what is it asking me? Then you've got to pick the equation that suits that. So you've got to pick the equation that has everything that you have and also has what you need. So if you're going to solve for displacement, you can't use the top equation because it's not there. You may have to do this in steps as well. So we'll go through a couple of examples and you come to get what I mean by that. So look at our first example. Now these are actually taken out of the book, so you can follow along if you like on page 58 and 59. Okay, the first one, I've just condensed the question down to their kind of core information. Okay, example 3 from the book. An airplane has initial speed of 75 meters per second. It comes to a halt. You got a question, San Diego?
Yeah. Which one's which for the equations?
Which one's which? 1, 2, 3 in that order. Yep. It doesn't actually matter if you know them, if you have access to them. I refer to them in that order. So if I ask, okay, which equation should you use, and I always write them in this order. You always see them in this order. So, but the order itself doesn't matter. You would always just pick which is appropriate, which equation is appropriate. In other textbooks, you'll see them with other symbols, which I'll go through after I just do this demonstration. And they might be written in different orders and slightly different forms as well. So some courses do it differently, but I'm doing it the way Mr. Turnbull does. He uses V naught instead of U for initial velocity. But you notice the textbook does both. Okay, so let's mind this question for initial information. Any more questions before we go? No? Okay, let's just go through this first one. So this is on page, this is example 3 on page 58. Okay, I've condensed it down a bit. An airplane has an initial speed of 75 meters per second. It comes to a halt in 1.2 kilometers. Okay, so to start off, before we even look at what we're going to ask, let's write down what we know. So what do we know about this? So what quantities? Yeah, that's your initial, that's your V naught. 75 meters per second. Okay, what else do I know? And yeah, the final velocity is 0 meters per second. You don't have time. Yep. That is a distance, or in particular displacement. It's kind of traveling in one direction. You'll notice something about this that will come out in this question, in the first question, about vectors, if you do it right. But yeah, it is a displacement, but the idea is almost interchangeable because the airplane's only traveling in one direction. Okay, can we use 1.2 kilometers? What should we use? What's our standard international unit? Meters. Okay, so I'm going to write that down. I mean, you can write down 1.2 kilometers, but before you go and substitute, you must convert to standard international units. All right, so that's 1,200 meters. Okay, because that's important. When you start rearranging and solving for the unknown, because the first question is actually we're finding acceleration. Okay, so find acceleration. Acceleration is in meters per second squared. So if you mix up your distance units, kilometers with meters per second, you're going to come up with a unique unit for acceleration. That's not common. All right, so remember standard international units, particularly it's really important when you start mixing around with equations with all sorts of different variables. It's usually a given. Like you know you can do this with your speed equals distance on time. You can do distance in kilometers if you times in hours and then get a speed of kilometers per hour. But when it comes to this stuff, particularly acceleration, we've only really got one unit, which is meters per second squared. And other things that come into play with that, when we do forces, force equals, from Newton's second law, force equals mass times acceleration, like I went through the year 10s. Anywho, okay, so acceleration now. So that's what we've got. We've got V naught, we've got V, we've got S, and we want to solve for A. Okay, so let's have a look at our list. And just in the order we're given here, who can tell me which equation should I use? Number one. Let's have a look at number one. We've got V naught, we want acceleration. Do we have time? No. Can't use number one. Number three, yes. Because the problem is you don't have time. You could probably do it in a stage and work out time, because basically you actually can solve for the time using the first equation, then solve for, then use the second one. That's a very complicated way of going about it. Actually, sorry, no, you can't because you don't have acceleration. You actually have to go back to basics, and that's actually very hard. You could work out average speed and then do it. No, the most easy way is we're going to use the third equation. So we're going to use V squared equals V naught squared plus 2AS. Okay. So, what's, now, my physics teacher, when I did this, year 11, year 12, he always, but particularly the year 12 teacher, is the one who sticks in my mind. He had a particular way. You have to rearrange the equation first. Sometimes that's all right. Sometimes that's a good idea. Not always. Particularly when you start introducing zeros, it makes things very simple. When you put zeros in the equations and things cancel, it actually comes out quite nice. So for this instance, I'm actually going to rearrange it afterwards. Okay, so I'm going to do a substitution. Okay, so what's my final velocity? 0. Good. 0 squared equals, what's my initial? 75 meters per second. Yeah, you don't have to put units in when you just substitute, but you have to list your units afterwards. Okay, plus 2 times A, which I don't know, times by distance traveled, 1,200. Okay, let's just simplify that before we move on. So we got 0 squared is 0 equals 75 squared. Someone want to do that? So 75 squared.
5,625.
Thank you. Okay, then plus 2 times 1,200 is 2,400. Okay, now I need to make A the statement of the equation, so I'm going to move, I'm just going to write over this side. Let's continue it to the right. Okay, so I've got 2, 4, I'm swapping sides, and I'm also moving that, I'm moving this across the other side by subtraction. So hopefully you guys are all right with rearranging equations, because you're going to be doing a lot of it in this work. Okay, so we got that. Everyone happy enough with what I did there? I swapped the sides of the equations and I subtracted both sides by 5,625. Okay, last thing I need to do, divide by the coefficient of A. Okay, now you notice I'm going to get a negative. And we'll talk about that in a second. Someone want to just punch that out for me? Just realised I didn't bring my graphics calculator with me. I can't divide by 20. I don't know my 2,400 times tables.
Negative 75 over 22.
Do you want to put the F to D and just...
Negative 2.34.
Yeah, that sounds about right. Okay, I should probably check with the book. Yeah, 2.34, 3 significant figures. Okay, what's significant about the negative?
Decreasing.
Not necessarily decreasing, but it is in this instance. Now, remember we talked about with the velocity time graphs, like it is in this instance. It's decreasing because it has the opposite sign to the initial velocity. So you are right. That's not the most significant thing. The significant thing is the reason why it's negative is because it's opposite. But that implies that it is decreasing. But if you had minus, it means if that was minus, that would mean that would be in the same direction. Yeah, but no, you're right as well. It is decreasing. Yeah. So time taken to come to a stop. That's the next one. Now, as a general rule, if you can find an equation to solve this using just the initial information, I'd recommend it. That's usually a given, because if you make a mistake here, that will follow you through later on. But you notice that all these equations have acceleration in them. There is a way to do it without acceleration, but you have to go back to the kind of the core information we went through at the start. But we're just going to use these 3 equations for now. You can get more tricky later. All right. So, and what I would suggest is you take the when we've written down 2.34. What you should probably use in the when you substitute into your calculator is a value which that you still had in the calculator without rounding. Okay, but let's have a look at our equations. Okay, so the initial information we had was v and v naught, and we've worked out a, so we can use this one to solve for time. Okay, you can use the other one, but this one's harder because time's in 2 places. And that's not a nice one because, initial velocity is a non-zero value. So basically you're solving a quadratic equation by doing it that way. So let's not do it that way. Let's take the first equation. Someone already done it? Okay, so equals 75 minus 2.34 times by time. Rearrange that. 2.34, I'm actually moving this across, equals 75, and time equals 75 divided by 2.34. If the last thing you did in your calculator was to work out, sorry, you can't see that? There we go. Okay, if the last thing you did was to work out the 2.34 on your calculator, do 75 divided by shift answer. Pardon? Negative 32? Oh, yeah, I know why. Sorry, that's because you got a negative answer in your, the last thing you got is negative, yeah. So it should, did you notice how I've moved it across so it's positive? But you can interpret that in your head and then just go, sorry, it was 32 seconds? Okay, there you go, 32 seconds. All right. Okay, so there's that one. Does anyone have any questions about that problem? Yep, sure.
Why did you change the 2.34 to minus? Is that
Oh, no, see, it was a minus here?
yeah.
Okay, now in the rearrangement of the equation, you notice how they're both on the right-hand side? Okay, so what I did basically, I didn't actually swap the sides of the equation, I actually literally just added 2.34t to both sides. So that's why it's on the left-hand side and the 75 is still on the right-hand side? Yeah. So, no, well, okay, guys, just pay attention. That's a good question. Some of you are going to have different ability levels with rearrangement of equations. Okay, when you see an equation, just for general, I'll help people out who have trouble with rearranging equations or understanding what has been done with rearrangement of equations. The way I like to think about it, you guys remember playing Pass the Parcel in primary school? Okay, you see, imagine in your parcel is like your unknown variable, and all right, someone's gone and put layers on that, and your layers is your bod mass or your bed mass. So there's all those operations you've done to the unknown variable. Okay, but in this case, we've put numbers in here, so there's only one thing to solve for. So what you've got to do is when you play pass the parcel, you undo the outside first. So if you look at the equation, if you look at this equation here, what's the last thing that happens to t? I'll rewrite it so that makes it a bit more obvious. This will make a bit more sense this way. Okay, so all I've done is just rearrange how that's written. What's the last thing that happened to t? So 3.4t. So if I have minus 3.4 times t plus 75, what was the last thing that happens in your BODMAS operations? Plus 75. So that's the first thing you undo. So, but what I actually did was I actually didn't do that. I actually added it to both sides. But the idea is you've got to get that across the other side, or they have to be in separate sides. So you can't divide. I suppose you can, but you have to be careful what you're doing. Generally how you undo equations is you unwrap them in the reverse order. So the first thing that happens to t is you multiply by minus 2.34 in your BODMAS rules, because multiplication comes before addition. So then when you undo it, you've got to undo the addition subtractions before you undo the multiplication divisions. Does that make sense? Yeah, and if you've got powers in there, well that's a lot. If you've got powers acting on t. So it's all that balancing equations basically. This stuff you should be pretty good at with your mathematics, but I know people got different ability levels. All right, now, so you have opportunity to practice that, but I'm just going to move on to the next question for now. Okay, so a car starts from rest and accelerates for 10 seconds until reaching 20 meters per second. It travels at a constant speed for 2 minutes and then brakes to a halt in 3 seconds. Okay, now you can follow along with this question on page 59. You don't necessarily have to copy it all down. You can get that out of your book, but I'm going to go through it. Now, the thing is about why I use this one as an example is this is now telling a more detailed story. We've got a car accelerating, then at constant speed, and then it's actually coming to a halt, so it's decelerating. So it has a different form of acceleration. You can imagine drawing that as a velocity time graph. You have a relatively steep slope going up, and then a straight horizontal line on your velocity time graph, and then a quick motion downwards. Okay. All right, so the car starts from rest and accelerates for 10 seconds. All right, so basically we're going to deal with this in parts. So we're going to deal with the first 10 seconds and then the next 120 seconds. So you see what I've done there? 2 minutes, 60 times 60. Yeah. And then finally the last 3 seconds. Okay, now the question is asking, sorry, I actually didn't write the question in here. Find total distance traveled. So I didn't actually write the question. Yeah, find total distance traveled. To do that, I have to work this out in 3 parts. So you guys see that all right? Yeah. So some people are just having trouble. Yeah, you don't have to necessarily copy this down. It's in the book as well, page 59. It's written up a bit better than I've done it because it's printed. Okay, but I'd like to just show you what I'm doing. Okay, so for the first 10 seconds, all right, we don't know the acceleration, but we do know how the 10 seconds, it starts from rest, and then it has a final velocity of 20 meters per second. All right. So I'm going over my margins. Okay. Now, you can go and work out the acceleration and then work out the distance by using these equations. But it's actually probably better for this one, and you'll see that what they've done in the book as well. So I'll move this down a bit. Okay, what they've actually done is they've just used the distance formula like I did over here. So they've used this. Okay, so they've used the average velocity, and then they've worked out, so I'll just do that in parts. I'm just going to work out the average velocity. 0 plus 20 on 2 equals 10, and then distance equals average velocity times by time, which is average velocity times by time. 10 times 10 is 100 meters. Yep, that's correct. Okay. All right. Now, the second part's pretty easy. because we know how fast we actually travel in that section. So the second part is you're at constant velocity, so thereby you carry over your final velocity from the acceleration, and that's how fast you're traveling for 2 minutes. So that's simply distance equals speed times time. So 20 times by 120 is 400 meters. Everyone happy enough with that? Yeah, question? You just couldn't see it? Okay. That one's easy. Now the last one, 3 seconds would come into a halt, so let's write down the final velocity is 0, initial velocity is 20. Sorry, move that over. And we don't know the acceleration. So this is another one where we'll do it the same way as we did with the first part. You can work out the acceleration, but it's not actually something required of you. So it's probably better just working out the average velocity, which is again going to be 10, but it's just happening over a short amount of time. So V is yeah, we're coming to a halt. In the last 3 seconds, we're coming to a halt, and we're starting at 20. Sorry, V is the final, V naught is initial. Yeah, so it's like at the start of whatever time we're talking about. They do use alternate symbols in there. They use V and U. I'll write up the symbols in a minute, but I want you guys to try this yourself. Just start on some exercises and get your head around it. Okay, so displacement equals, finishing this off, 10 times 3 is 30 meters. Okay, add them up. We've got 100, we've got, the end of the day, you've got 100 plus 2400 plus 30 equals total S of 2,530 meters in total. Yep. You guys have enough of that? All right, leave it there. I think I've been chatting for too long. I'm going to write up a few things on the board, but if you guys want, just have a try on page 71, questions 16 to 21. Just for the moment, I'll probably set some more later on, but I just want to get you guys just playing around with this a little bit. And look, I'm going to cut off here, and you guys just have a try. Try for yourself.
What questions?
It's on the board.